Hello guys, thank you for coming to Olewave channel, and I wish you all the best for the coming Thanksgiving holiday, and best of luck to my Indian subscribers. And today we're gonna be reading a paper called Branchformer. It's a parallel MLP-Attention architectures to capture local and global context for speech recognition and understanding by researchers from CMU. And the advanced version of this work, which is E-Branchformer, a collaboration between the ASAP and the CMU. They have achieved I think it's the best or the state-of-art speech recognition accuracy on the deliberate speech task. Let me quickly go to the results section, and you can see that I think this was about 2 years ago. When the Google researchers, they worked out something called a conformer. I have a reading of the conformer. If you are not familiar with it, just search conformer in my YouTube channel. It's an Olewave channel. Search the conformer, and you can see that with the language model, Google guys can achieve a 2.1 percent accuracy error rate, while the original Branchformer didn't work much better than the conformer, roughly the same. But when they upgraded their stuff onto the E-Branchformer, the large model, the model is slightly bigger than the conformer. So I think this is a yellow flag to me, or it may not be a fair comparison. But you can see that the accuracy it dropped about 10%, at least 10%. I think it's 10% drop relatively. It get to 1.85, and once they apply their advanced language model, so this time is not very apple to apple comparison, because conformer definitely use something called a transformer LM, but this one is an advanced LM. They finally achieved the 1.81 in terms of the WER, and on the test adder, which is the noisier test set, they managed to get another 10% reduction from 4% to 3.65. This is very, very impressive, because I think I've seen lots of models which use the transducer architecture, which is streaming. The streaming model usually on the test clean they can only get 3.6 or something, but they can get test adder non-streaming version, they can put 3.6. Very impressive. But today we're going to be just focusing on the algorithm of the first paper, or the Branchformer. And you can see that I think the biggest contribution they have done was to introducing a sort of a branch style architecture. So instead of just having a single or main branch backbone network or feed-forward network, they managed to add a side branch. But eventually, the side branch will be merged back into the main branch. Okay, the side branch, they called it convolutional gating MLP, and it's supposed to extract the local relationship compared to the transformer, which compared to the conformer. Yeah, which compared to which is additional to the transformer main branch, which is supposed to capture the global relationship. Okay. Well, you can see the results on their even they're not doing the advanced version of Branchformer. The Branchformer itself, so on the AI shell, is a Mandarin speech recognition task, Mandarin read speech. They are able to beat the conformer model by about 10%, 10% or 5%, maybe 5%. Okay. But while you can see that transformer is way behind the Branchformer and the conformer, so I think it's time to remove the transformer based encoder out of the league of sort of speech recognition models. And you can see also the cgMLP model they introduced a side branch. Their ASR does not totally rely on the side branch. It has roughly the same performance as transformer. Interrupt me if you have questions, okay? And the author, the first they reviewed the conformer and they raised the question because conformer definitely explore the local and global relationships. Remember, they have the macron style network, right? They have self-attention layers and convolutional layers stacked on top of each other. So that means in the conformer model, the local and global relationships are exploring they are exploring both local and global relationship. Because if you think about anything that's convolutional, remember anything that's convolutional things module, it explores the local relationships. You ask me why? Okay, just search these things on the Medium. They have tons of tutorials on talking about CNN, local context stuff. Okay. Uh-huh. Oh, I understand. Okay, I see what you're saying. How you're asking me how the input was organized into the neural networks. To answer that question, the quick answer is in speech recognition, people do framing. So they have a moving window to crop the wave segments, okay, as into samples of samples and samples. So it's not sending the whole waveform into the neural network. Is that clear to you? Left and right, people, when they're doing this type of libre speech recognition or red speech recognition, people usually they merge the two channel into single channel, mixed. Yeah. For I see what you're saying. But the short answer is you definitely can have two encoders for two channels. Suppose you're having a microphone array of two microphones. The long answer would be it's not very related to our Branchformer paper. So I would recommend to watch more tutorial video that I have on the channel, including the transformer. I think I have a very detailed explanation of how the end-to-end speech recognition works using the example of a transformer. Okay. Yeah. But any questions related to Branchformer is welcomed. So the author asked, since Conformer already explored the local and global relationship, but there's no clear answer of whether they are equivalently important. So if not, how should you adjust your operation to make sure that this thing is working correctly? Okay. And the authors, they are saying they are trying to explore this, but my personal opinion is that they do not fully answer the questions, but I would agree that it's also very important for them to raise this question. For people who raise the question is sometimes more important than resolve the question. So they propose this branch style conformer, and you can see that it's a fairly so this is, you can see that this probably answer Asher's question, the audio sequence, the front end. If you're not familiar, you want to know more about the front end, I would just recommend you to check some paper called Conformer, maybe Conformer. They talk a lot about the front end. Maybe Transformer. Okay, I have Transformer. I have the tutorials in my channel. And convolutional subsampling. This is also a standard configuration in the speech recognition now. And the positional encoding, this is borrowed from Transformer. And they, on top of this, they stack n blocks of Branchformer. And you may ask, how does this network structured? And you can see that on this side, let's come to the right side. You can see on this side, on the left side, this is exactly Transformer. Are you with me? Okay, this is exactly. Yeah, actually, I may sound rude to you. I'm sorry about that, but this is fundamental things in the Transformer. You should read watch my video, because if I keep explaining the simple things here, I wouldn't be able to finish the video today. Yeah. But so my recommendation is, why don't we just wait me finish everything, then you ask question. Okay, I'll give you 5 minutes. There. So on the left side, you can see it's definitely Transformer. On the right side is something new. It's even new to me. I never know what is cgMLP. And you can see they have the equation in this section. But I will forget about the equation, but just show the flow chart to you. So there's nothing new about layer norm. Just try to norm the input. And the channel projection, I think it's a fairly linear thing, right? And the Jiru activation is not fancy stuff. And the only thing here, you can see here, and you can see the convolutional spatial gating unit. First of all, it has this Resnet connection style. Anything that goes this way and have a side loop, then go back in, it's a Resnet style. Although, people sometimes do not mention this is Resnet, but this is Resnet style connection, because the residuals, they use the residuals. And again, they have a norm here, and they have this depth-wise convolution. This thing, remember, anything that's a depth-wise convolution, when that thing is being used, it is supposed to explore the local context, or the samples in a local range, in a certain context range. It tries to explore the correlation between these samples. Okay, and then it's fairly straightforward: channel projection, then dropout, and then later on they merge and project. So you can see this is why they call their stuff a Branchformer. So this is their main branch. I think they didn't call this side branch. I would call them side branch, because they heavily rely on this main branch. But this is like a subsidiary branch to the main branch. You will see later on. And you can see this is the equation. I'm definitely sure that as long as you just check the math here, you will be able to understand it. I don't think you have any difficulty understanding this. But just to remember that why you ask why they use something called MLP, I think because they also mentioned that they want to have they want to convert the non-fixed length input into fixed length input. So they need because MLP can only take fixed length input, but I think this convolutional gating MLP is capable of taking variational input length, because speech, is never fixed length, right? But the image is definitely could be fixed input, right? Fixed length. How about NLP? NLP is difficult too. Yeah, if you are asking me to read this paper, I can do that for you, but this is not the focus today. But you can definitely, let's go back to the picture again. This side is definitely the self-attention thing. Let me use a blue pen here. Self-attention thing here, and this is a convolutional thing right over here. So you can see in the conformer, the two things are being stacked on top of each other, right? The self-attention, I think either on top or on bottom, right? I forgot. Let's say it's a convolution on the bottom. See, this is a sequential, but these things, they're parallel to each other. So this is why the paper's title has the parallel here. But you may ask, why this is better than the stacked on top of each other? The author, I would say, they're saying that I think they use a lot of text to explain this thing, but my summarization of their text is that having two separated branches allows them to separately model the attention-based information and the convolutional-based information. And then when you're doing these two things separately, you are capable of better modeling each of them. And then finally, you have this ensemble model, right? You can see that. The equation merging project. Let me show you. So this is the standard way of doing things, right? Concatenate, then have a projection. The attention output, the MLP output, concatenate them, then multiply that with a matrix. But the authors are very smart. They come up with something manually tunable. So instead of having this type of matrix, which is hard to tune, anything that's with this matrix, that will be automatically learned. You cannot manually tune by yourself. But instead, they come up with this. See, they have using a projection matrix to the output of the attention, and also output a matrix to the MLP output, and then apply a softmax. They got two scalar values. So say the attention value would be 0.3, MLP model would be 0.7. These two things add up to 1. So this will be a scalar. So having a scalar here would allow them to better understand what is happening here. Because when you have a matrix, it's full of numbers. You cannot see them. But with this, they can see, okay, they can see whether the neural network model would weigh attention more or MLP side more. This is a convolution. Better to use a convolution here. Whether the convolution would be more important. Okay. And you can see that the merged one is is no longer a concatenation. It's a weighted sum. Okay. Fairly smart. Okay, let's look at some of their analysis. I skipped the faster former. But those are very interested. I think this is by Google, right? Faster former. It's fairly popular now. But I'm not not a fan of the mass of the fast former. Although it's fast, but I think the performance is not very good. So I'm not a personal fan of it. But in case you care about training speed, you probably want to play with the faster farmer. This is again, they talk again about the ASL results. I think you can see that they do better than the conformer. Slightly better, I think. Not a lot better. But think about, but even it's not a lot better, I think they can still argue that people should not still use the conformer. People should switch to the benchformer because the model size is roughly the same. There's no reason for you to stay at the conformer. Even the improvement is small, like 5% relatively. And the experimental setup. Yeah, I think lots of people are working on the English, so they want to see the results on the English. So this is a switchboard, telephony task, telephony speech recognition, dictation task. And this is still better. You can see that, right? Especially so this is the weighted sum of these two numbers, weighted sum. And you can see SWB is an easier task, less noisy. And the CHM is the more noisy one. You can see for the more noisy one, it's better than conformer, but on the less noisy one, it's not much change. The model size is roughly the same. And they check it on the LibreSpeech ASR task. And you can see this is, a lot of people would agree with me, especially the speech researchers. This is a mystical baseline which nobody except the Google can reproduce. I have lots of people who try this. Most times they can only get something like, yeah, you see, the Canada guys, SpeechBrain, they can only get 2.5, and ESPNet can only get 2.52. Yeah, I always just got 2.5. I cannot get 2.1. But these authors, they tried reproduce on the ESPNet. They also got 2.5 with the conformer. But when they play with the branchformer, I think they released their code. You can play with it on their ESPNet. You got 2.4. Yeah, it's slightly better than conformer, okay? But still not 2.1 yet. And they also play with on the SLU task. I'm not an expert on SLU, spoken language understanding, and I would think that, to me, so the current SLU training set and also test set are relatively very small in my personal opinion. But you can see definitely, I would believe those results are significant, okay? The improvements are significant. You can see that the conformer versus conformer, right? The backend, the language understanding part should be the same, but the ASR part would be different as an improvement. And here are the results on this is still SLU. And you can see that the branchformer's F1 is over here, and the conformer is roughly here. I wouldn't see much difference, okay? Yeah, we'll just skip this. Google Speech Command, come on. This is a very small test set. I don't think they also should play with this. What's the difference between 0.74 and 0.73? Might not be even significant. But this test set, I would say, is very popular. I think lots of people who start with the speech recognition would play with this one. It's free, small. You can play with even on probably on your CPUs to train the model. Okay, here they compare this thing with a Fastformer. I'm not very interested. Okay. Well, it's good to know that when you play with a Fastformer, okay. So what they mean by Fastformer is that, remember, the main branch is composed of blocks with the self-attention layers in it. They replace that with a fast attention, something like this. Okay, so they reduced the complexity from by t over k. It's probably 2 to 10 times reduction, probably. You can see that the increasing in the word error rate is not that much, but this does not have anything to do with branchformer. Okay, just to show that the Fastformer was effective. I think it's not very relevant to this work. Here is something I really interested, because if you check the figure number 5, this is very, very interesting, I would say. This is a visualization of branch weights in the Branchformer with different sizes on different data sets. First, let's see the AI shell. Layer 0 means the bottom layer, right? Bottom layer. And the layer 23 or the 24th layer means the layer that's output something that would be used by the subsequent decoder input. Okay. So definitely we check from here. You can see that for all the 2 configurations of AI shell and the configuration for the switchboard, Mandarin, English, red speech, dictation of the spontaneous speech, over the last layer, what you can see, the weights of the cgMLP or convolution takes 95% or even 90%. What does that mean? That means in the final layer, or in the final layer, the model would weigh the convolutional side more. It's fairly compliant with my or people's common sense. Because of why? Because everybody knows that the attention style of the speech is a monotonic. For those of you who does not know what I'm talking about, please check the transformer tutorial. It's a monotonic attention. That means if you draw a attention hot map, you will see as long as I speak, the attention weights or the heavy attention weights would move along with my speaking. Okay. So it's unlike the machine translation, the attention will go back and forth. So this is why eventually for the speech recognition, the local attention, or the local contextual information would be more important in decoding the correct stuff in the speech recognition. So this makes sense. The convolution things dominates in the end. But the interesting thing is in the middle layers, the importance interleaved, and lots of time it's getting over 95%. It's not 50-50. That's this stuff. And also why the interleaving is stuff is here. They also, I don't think they give any a detailed explanation why the interleaving weights were showing up to here. And I'm still in the process of assimilating their stuff. But once I figure out something, I will definitely let you guys know. Okay. This layer, diagonal self-attention, yeah, this is not very important. Not important either. All right, I think I'm gonna stop here today, and thank you for stay with me, and thank you for your patience, and I will see you 2 weeks later, and please keep tuned. Let's subscribe our channel and share the video with your friend. Thank you.